Hello everyone. In this lecture, we have to discuss about characterization of nanoparticles. Okay, as you may get while we have to synthesize nanoparticles, it is necessary to identify or characterize the nanoparticle that the nanoparticle form or not form, and what kind of nanoparticle are formed, and what is the size of nanoparticle, what is the shape of nanoparticle. Okay, so there are so many parameters which we have to analyze while we have to working on the synthesis of nanoparticle. Okay, and the process of identifying shape, size of nanoparticle is called characterization of nanoparticles. Okay, there are many techniques that have been used. Now for the characterization of nanoparticle. So we have to discuss in this lecture the application of these various techniques that would be used for the synthesis of nanoparticles. Okay, these are the learning objective of today's lecture. To know about nanoparticles, nanomaterials, and to understand the process of characterization of nanoparticles, and to know about various types of methods that will be used for the characterization of nanoparticles. So, characterization of nanoparticle refers to the study of nanomaterials, including their feature like composition or structure or various other properties like physical properties, electrical properties, magnetic properties, optical properties. Okay, so the process of identify these properties is called characterization of nanoparticles. Okay, and why the characterization of nanoparticle is so important? Because nanoparticle properties vary significantly with the size and shape. Okay, that's why it is essential to measure the size, shape of the nanoparticles or synthesized nanoparticles. Okay, and accurate measurement of nanoparticle size and shape is essential, therefore critical to its applications. Okay, so because the applications of these nanoparticles solely depend on its shape, size, physical property, chemical property, composition, electrical property, magnetic property, optical properties. Okay, and what are the methods that could be used for the characterization of nanoparticles? Okay, so there are two broad types of methods that can be used for the characterization of nanoparticles. The first is microscopy and another is spectroscopy. Okay, so microscopy like scanning electron microscopy, transmission electron microscopy, uh, scanning tunneling microscopy. Okay, so these type of microscopy can be used for the characterization of nanoparticles. Okay, and if we talk about the spectroscopical techniques, so these are the some of the techniques which we can use for the characterization of nanoparticle like XRD, that is X-ray diffraction technique, small angle X-ray scattering technique, X-ray photoelectron spectroscopy, UV visible spectroscopy, Fourier transform infrared spectroscopy. Okay, so first of all, we have to discuss various types of microscopy and their applications along with their working principle. So the working principle of transmission electron or scanning electron microscopy are almost same. So when the beam of electron strike the surface of the specimen and interact with the atoms of the sample, signals in the form of secondary electron, break scattered electron, okay, and characteristics X-rays are generated that contain information about the sample surface topography and composition. Okay, so this is the principle which we have to exploit for the characterization of nanoparticles. Okay, as in this figure, you have to see that this is electron gun. Okay, and which produce electron beam. Okay, and this is anode. Okay, particularly made up of magnet. Okay, and this is a magnetic lens. Okay, and the electron beams pass through the magnetic lens. Okay, and this is scanning coil. Okay, and this is a big scattered electron detector. Okay, and this is stage or this is the sample put on for the analysis. Okay, and this is secondary electron detector. Okay, this is scattered electron detector. This is secondary electron detector. Okay, so by the analysis of these backward scattered electron detector and secondary electron detector, we have to analyze the topography of the specimen. Okay, so what types of features we can analyze by the use of scanning electron microscopy. So we have to analyze texture and surface of the sample. That means topography of the sample. We have to analyze size, shape, order of particles. That means the morphology of the sample, and the composition or elemental composition of the sample we can analyze, and crystalline structure, that is arrangement of atoms and molecule in the sample we have to analyze. Okay, what is the operational mode of scanning electron microscopy? So there are three kinds of mode by which we can operate scanning electron microscopy: the primary, secondary, and tertiary. Okay, so primary means high resolution, that is 1 to 5 nanometer up to it has, and secondary electron imaging. Okay, and the secondary operating mode is characteristic X-rays and identification of elemental composition of the sample by EDX technique, and tertiary back scattered electron imaging through to the elemental composition of the sample. So these are the three ways by which we have to analyze our sample under the scanning electron microscope. So you have to see that how these would be arranged. So this is electron gun, okay, by which the electron beam generated, and this is condenser lens, and this is magnification control, okay, three scale files, and this is objective lens, okay, and this is amplifier, okay, and this is sample, and finally the on the display we have to obtain the electronic image. So this is electronic devices that used to detect and amplify the signals and display them as an image on a cathode rays a tube, in which the raster scanning is synchronized with that of the microscope. Okay, so in a typical scanning electron microscope, the beam passes through pair of scanning coil or pair of reflector plates in the electron column to the final lens that could detect the beam horizontally and vertically. Okay, that give the image, and image display. Display is therefore a distribution map of the intensity of the signal being emitted from the scanned area of the specimen. Okay. So what is the advantage of use of scanning electron microscopy? So the bulk sample can be observed and larger sample area can be viewed under the scanning electron microscopy, and it generates photo-like image, and very high resolution images are possible by the use of scanning electron microscopy. And in scanning electron microscopy can yield valuable information regarding the purity as well as degree of radiation. And there is apart from advantages, there are many disadvantages there. Like a sample must have surface electrical conductivity, and non-conductive sample need to be coated with a conductive layer. Like most of the time, the gold layer covered on the sample to be analyzed, and it will be time consuming and expensive. And sometimes it not be possible to clearly differentiate nanoparticle from the substrate, and scanning electron microscopy can't resolve the internal structure of these domains, because most of the time the surface morphology we have to analyze by the use of scanning electron microscopy. So this is the structure of the transmission electron microscopy. Okay. So what characterization of what type characterization we have to carry out by the use of transmission electron microscopy. So we have to analyze morphology like the shape, size, and order of particle in the sample by the use of transmission electron microscopy. And we have to analyze crystalline structure of the sample or arrangement of atoms in the sample, and we also have to analyze defect in the crystalline structure by the use of transmission electron microscopy, and composition or elemental composition of the sample we have to analyze by the use of transmission electron microscopy. And this is the structure of transmission electron microscopy, in which the crystalline sample interact with the electron beam mostly by deflection rather than absorption. So the intensity of the deflection depends on the orientation of the plane of atoms in a crystal related to the electron beam, and a high contrast image can be formed by blocking deflect electrons, which produce a variation in the electron intensity that reveals information on the crystal structure of the nanoparticles. And transmission electron microscopy image can generate both bright or light field or dark field image. And so this is the figure which demonstrates the arrangement of various elements in the transmission electron microscopy. This is electron one, which produces the electrons beam, and this is anode, and this is condenser lens, and this is a specimen, and this is objective aperture lens, and this is intermediate lens, and this is projector lens. Finally, on the fluorescent screen, we have to get image of the specimen. So these types of image we have to obtain by the electron microscopy. Okay, this is myxovirus, this is fluvirus, okay, this is collagen fiber, this is herpes virus. Okay, and we have to obtain transmitter image by the standard transmission electron microscopy. This image we have to get by high resolution transmission electron microscopy. Okay, and we have to see that this is copper oxide nanoparticle, this is silicon. Okay, so you have to see that by the use of standard transmission microscopy, there are image is not have much contrast, and here you have to see that the high resolution image by the use of high resolution transmission microscopy, in which you have to see that difference between the both images. Okay, and this is transmission electron micrograph of isotactic polypyrene particles. Okay, this is the Syria nanoparticles. Okay, and this is small Syria nanoparticles. Okay, so these all are the image for transmission electron microscopy. And what are the advantages of use of transmission electron microscopy? So additional analysis technique like X-ray spectrometry are possible with the use of STEM, and it is high resolution, and 3D image construction possible but aberrant, and change in the nanoparticle structure as a result of interaction with a gas, liquid, and solid phase substrate that can also be monitored. And apart from advantage, there are disadvantages also there. Like sample must be able to withstand the electron beam and also the high vacuum chamber. Okay, that's why it is techniques which can be utilized for the visualization of image, which can might withstand with the electron beam and high vacuum, and sample preparation necessary, mostly used for 2D image, and it is time consuming. So, now what is the difference between the scanning electron microscope and transmission electron microscope? Scanning electron microscope has high resolution of bulk specimen, loading to make sample thin, and transmission electron microscope require high resolution of thin specimen, and 20 to 50 angstrom the most commercial instrument, less than 10 angstrom for the research instrument, and transfer electron microscope 1.2 and 1.5 angstrom most commercial instrument, and 3D appearance of the specimen image as a result of the large depth of the field, and technique that provide crystallographic structure information like lattice arrangement, orientation, relationship, dislocation. Okay, while it is capable of window magnificence, complement the information available from the optical image. So, how we can synthesize an optical characterization of copper oxide nanoparticles? Okay, so this it figures for the scanning electron micrograph of a prepared copper oxide nanoparticle. It shows that the copper oxide nanoparticle are in rectangular shape, and this figure shows the transmission electron image of prepared nanoparticle, and the size of particle observed in the transmission electron microscope image is the range of 5 to 6 nanometer, which is a good agreement with the calculated by Shigita formula using XRD. And this figure shows the selected area diffraction pattern of a prepared copper oxide nanoparticles that shows that the particles are well crystallized, and the diffraction ring on a SAED image with the peak in the XRD pattern, which also proves the monoclinic structure of a prepared copper oxide nanoparticles. That's why characterization technique is very important phase of while we working on the nanoparticle synthesis. And the next is scanning tunneling microscopy. Okay, and scanning tunneling microscopy based on the concept of tunneling. When a conducting tip is brought very near to a metallic or semiconducting surface, a bias between the two can allow electron to tunnel through the vacuum between them. Okay, and variation in the tunneling current is the probe pass over the surface are translated into the image, and the scanning tunneling microscopy normally generate image by holding the current between the tip of the electrode and the specimen at the some constant value by using piezoelectric crystal to adjust the distance between the tip and the specimen surface. Okay, so that's why the technician which know how to operate this is required for the analysis or handling of the scanning tunneling microscope. So this is the way how it works. Okay, so you have to see that this is a piezoelectric tube with electrode, and this is a tip, and this is sample. Okay, and this is tunneling voltage, and this is tunneling current amplifier, and this is distance control and scanning unit. Okay, that is data processing and display, and this is image high oriented pyrolytic graphite sheet under scanning tunneling microscopy. Okay, you have to see that how clear image you have to obtain by the use of scanning tunneling microscopy. Okay, and resolution is zero point 0.1 nanometer, and depth resolution is 0.01 nanometer. Okay, so it is high. It has high resolution as compared to the scanning electron microscope and transmission electron microscope. So this is image of scanning tunneling microscopy image, and advantages of scanning tunneling microscope image. Very high image resolution that capable of seeing and manipulating atom, and scanning tunneling microscopy can be used not only in the ultra high vacuum but also in air and various other liquid or gas at ambient and wide range of temperature. And disadvantages there like radius or curvature of tip extremely sensitive to the ambient vibration, and scanning tunneling microscopy can be challenging technique as it requires extremely clean surface and sharp depth. Okay. Now optical spectroscopy. So optical spectroscopy could be used the interaction of the light with the matter as a function of wavelength or energy in order to obtain information about material. As you know that each sample can absorb light of characteristic wavelength. Okay, so this phenomena can be exploited in the optical spectroscopy, and it has a typical penetration depth in is of order of 50 nanometer. And optical spectroscopy is attractive for material characterization because it is fast, non-destructive, and high resolution technique. So the first of your technique is X-ray diffraction. Okay. So X-ray diffraction can be used to look at various characteristics of the angled crystal or polycrystalline material using the Brake's law. Okay. So X-ray technique work on the Brake's law. Okay. To see that how we have to apply brakes no hair. You have to see that this is a wavelength of incident X-rays. Okay, and this is incident X-rays. Okay, of a particular wavelength. Okay, and this is atomic scale crystal lattice plane. Okay, then when this rays pass on, it reflects at a certain angle. Okay, let me say that it reflects at a certain angle. Okay, so by obtain the angle of reflection, we get knowledge about the lattice structure of the crystal by the use of X-ray diffraction technique. So the characteristics of X-ray diffraction technique are the lattice constant and d spacing. Okay, this spacing. Okay, spacing between the layer and the crystal structure. Third, crystal structure and thickness, and sample orientation, particle size. Okay, that's why XRD is time consuming and require a large volume of sample, and smaller crystal produce broader XRD peaks. Okay, this can be verified by the use of Schreier formula T equal to K lambda upon V cos theta, where T is thickness of crystalline structure and K is a shape constant, lambda is wavelength, okay, and V is FWHM, and theta is Brake's angle. Okay, and the next technique is small angle X-ray scattering technique. Okay, SAXS. So SAXS, small angle X-ray scattering, is the another technique that utilize scattering due to the existence of inhomogeneity region of the size of several nanometer to several tenth nanometers. And the characterization of this technique are particle size, specific surface area, morphology, porosity, okay, and fluctuation in electron density over length on the order of 10 nanometer or larger can be sufficient to produce an appreciable scattered X-ray density at angle 2 theta, which is less than 5 degree, and it is capable of delivering structural information of molecules between 5 and 25 nanometer of repeated distance in partially ordered system of up to 150 nanometer. Okay, and this is the instrument of X-ray photoelectron spectroscopy (XPS). Okay, where this is X-ray source, this is ion source, and this is SINS analyzer, and this is sample introduction chamber. So what is the applications of XPS technique? We can have to focus on the application part. Okay. So what element and the quantity element of the sample surface up to 1 to 12 nanometer, and contamination in the surface or the bulk of the sample, and empirical formula of the material we have to determine, and the chemical state identification of the element in the sample we have to determine, and the binding energy of electronic state we have to determine by the use of XPS applications, and the thickness of different material we have to determine by the use of X-ray XPS technique, and the density of electronic state we have to determine by the use of XPS technique. So XPS is routinely used to analyze inorganic compound, metals, semiconductors, polymers, ceramics, and even all the organic chemicals are not literally analyzed by XPS, okay, because they are readily degraded by either the energy of the X-ray or the heat from monochromatic X-ray source. Okay, that's why it is commonly used for inorganic compound, metals, semiconductor, polymers, ceramics. Okay, and UV visible spectroscopy. And this technique involves the absorption of near UV or visible light, and one measure both and intensity and wavelength. Okay, and it is usually applied to the molecule and ionic ion in the solution. Okay, as we know that UV visible spectroscopy work on the principle of light, that any substance or any molecule can absorb a specific wavelength of light, okay, and any molecule can absorb maximum light at a particular wavelength, okay, and this absorption of light is directly proportional to the concentration of the substrate, okay. So that's why we have to analyze the concentration of the given substrate, as absorption is directly proportional to the concentration. Okay, and that's why A equal to A directly proportional to the concentration. Okay, and A equal to A into B into C, where A is the absorbance, and B is the path length, and C is the concentration. Okay, and this alpha is the absorptivity constant. Okay, here we have to see that A equal to minus log I upon I zero. Okay, I is the incident light. Okay, and I zero is the reflected light. Okay, so because the incident light intensity and reflected light intensity are different. Okay, so that's why this is called Beer-Lambert law. Okay, so where absorbance is directly proportional to the concentration. If the molar extinction coefficient, that is alpha, is a constant for a same substance, and path length is the same for analysis, like QA, we have to use same QA for the different concentrated sample. So at that time, the absorbance of the sample is directly proportional to the concentration of the analyte. Okay, so that's why like this technique can be exploited for the identification or determination of unknown analyte concentration. Okay. So, and by the use of this technique, we have to get the absorbance at different wavelength, and this is called absorption spectrum that we have to analyze. Okay, and below that, the peak is the characteristic feature of a nanoparticle. This peak created due to the surface plasmon resonance in the nanoparticles, and when these nanoparticles absorb certain wavelength of light, so at a certain wavelength, it absorbs maximum light. Okay, that's why we have to obtain the peak. Okay, and by the observation of this peak, we have to identify the nanoparticle and the size of nanoparticles. Okay, and we have to compare the spectrum with the standard spectrum, and we have to identify the nature of the analyte. And next is the infrared spectroscopy. So, infrared spectroscopy, firstly, molecules and crystal can be thought of as a system of bonds, atoms or ions connected by springs. Okay, and these systems can be set into vibration and vibrate with a frequency determined by the mass of bonds, that is atomic weight, and by the stiffness of spring. Okay, that is bond strength. Okay, so this characteristic of atoms or molecules can be exploited in the infrared spectroscopy. And with this oscillation of the system, a impining beam or infrared EMR could couple with it and be absorbed. and this absorption frequency represent excitation or vibration of the chemical bond, and thus are specific to the type of bond and the group of atoms involved in the vibration. And in an infrared experiment, the intensity of beam of infrared is measured before and after it interact with the sample as a function of light frequency. Okay, so this is a technique utilized for the characterization of nanoparticles, and by the use of this technique, we have to identify the functional group that could be attached with the nanoparticles while we go for the synthesis of nanoparticles. Okay, so by the use of nanoparticles, we have to analyze the composition of the sample, concentration of the analyte, atomic structure of the sample, and surrounding environment, atomic arrangement. Okay, so the mechanical, molecular, and crystal vibration are very high frequency, ranging from 10 to the power 12 to 20 to the power 14 hertz. Okay, approximately 3 to 300 micrometer wavelength, which is in the infrared region of the electromagnetic spectrum, and the oscillation induced by certain vibrational frequency provide a means for matter to couple with an infining beam of infrared electromagnetic radiations and to exchange energy with it when frequency are in resonance. Okay. So that's why we need to understand the principle behind the infrared spectroscopy. Okay. So any molecule or crystal can be thought of as a system of bonds. You know that EV system made up of atoms or ions that connected by a chemical bond. Okay. So when these systems can be set into vibration, or when there is vibration on the exposure to the infrared electromagnetic radiation, and it vibrate with a certain frequency according to their mass or atomic weight, and their bond strength. Okay, so these oscillation of the sample spinning beam of infrared could be coupled with it and be absorbed, and this by the and we have obtained a certain peak in the a certain spectrum, and by the analysis of this spectrum, we have to analyze the types of functional group that could be attached with the nanoparticles. And these absorption frequency represent excitation of vibration of the chemical bonds, and thus are specific to the type of bond and the group of atoms involved in the vibrations. Okay, so it totally depends on the which atoms involved in the vibration, which functional group involved in the vibration. Okay, so that's why FTR is a technique that could be exploited for the functionalization of nanoparticles. Okay, so by the use of this technique, we have to analyze the functionalization of nanoparticles. Okay, and like in an infrared experiment, the intensity of a beam of infrared is measured before and after, and it interacts with the sample as a function of light frequency. Okay, so in this technique, we have to use infrared electromagnetic radiations. Okay. Now, UV spectroscopy. Okay, as we have to discuss that this UV spectroscopy are used for the analysis of DNA, analysis of RNA, estimation of protein. Okay, so these biomolecules can be estimated by the use of UV visual spectroscopy. Okay, but apart from this, this technique also we have to use for the characterization of nanoparticles. Okay, so that's why by taking spectrum of any nanoparticles. Okay, so we have to obtain. Okay, so this would give the first indicator that nanoparticle prepared or not. Okay, so this is showing the first indicator. Okay, and it denote the that the particle or nanoparticle in our solution synthesized or not. Okay, because we have to compare our spectrum with the standard spectrum. Okay, so each shape of nanoparticle has its characteristic spectrum, and each size of nanoparticle has peak at a certain wavelength. Okay, so we have to measure that. Okay, if there is contamination is there. Okay, so the peak may be disturbed. If there is different size is there, the peak is different. If even the concentration of a analyte or nanoparticle are different, so at that time the peak also at different wavelength. Okay, so that's why the shape of peak, the broadness of peak determine the uh, purity of nanoparticles. Okay, if you have to get only single peak in whole spectrum. Okay, so this shows that your nanoparticle is prepared in pure form because you have to get single peak. There is no other contamination is there. Okay, so by the use of this technique, we have to also analyze the purity of our analyte. Okay, so while this technique we have to analyze the purity of any sample, either nanoparticle, either any analyte like chlorophyll purification, compound isolation, compound purification, nanoparticle synthesis by the use of various biomolecules. Okay, so this could be exploit. This technique could be exploited for the characterization of nanoparticle along with the characterization of other analyte. Okay, and these are the reference. Okay. Now attempt quiz. So the first question is the functional group on the surface of nanoparticle can be determined by Fourier transfer, infrared spectroscopy, transmission electron microscopy, electron microscopy, and X-ray diffraction technique. Okay, so as we have to discuss in this lecture, the functional group we can determine by the use of Fourier transform infrared spectroscopy. Okay, and okay, so the correct answer is A, FTIR. Okay, and nanoparticle can be characterized by UV spectrophotometer. Okay, transfer electron microscopy, is scanning electron microscopy, Fourier transfer infrared spectroscopy, UV visible, and transfer electron microscopy, SAM, FCR, XRD. So, as we have to discuss in the lecture, there are all technical depending on the nature of analysis. We can be used for the characterization of nanoparticle. As you know that UV spectroscopy can be utilized for the identification of the nanoparticles and to check purity of the nanoparticles. And transfer microscopy used for the size of the nanoparticles and shape of the nanoparticles. Scanning electron microscopy can be used for the morphology of nanoparticles, topography of nanoparticles. FTIR used for the group for characterization of the nanoparticles. Okay, that's why all techniques could be used for the characterization of nanoparticles. And same electron used for the texture, surface, morphology of the sample, size, shape, order of the nanoparticles, and elemental composition of the nanoparticles. Okay, so, as we have to discuss in this lecture, by the use of scanning electron microscopy, we have to analyze texture of the sample, surface morphology of the sample, topography of the sample, size of the sample, shape of the sample, order of the particle of the sample, and composition of the sample, elemental composition of the sample. So, the option D is correct, and FTIR used for. So as we have to discuss that, FTIR used for the compositional analysis and concentration and atomic structure. Okay, so that's why Fourier transform infrared spectroscopy can be used for the either compositional studies and analysis of concentration and determination of atomic structure. That's why the option D is correct. And technique based on Pierre-Lambert law. So as we discussed in the lecture, the Pierre-Lambert law is that the absorbance of the sample is directly proportional to the proportional to the concentration of analyte. Okay, and this law is called Beer-Lambert law. Okay, the technique using this spectroscopy work on the based on the Beer-Lambert law. Okay. And spectroscopy technique used to analyze inorganic compound, metals, semiconductors, polymers, ceramics. Okay, so the most suitable technique to analyze inorganic compound, metals, semiconductor, polymer, ceramics is XPS. Okay, so the correct option is XPS. And crystal structure identified by scan XRD, X-ray diffraction technique, transmission electron microscopy, scan electron microscopy, Fourier transform, infrared spectroscopy. Okay, so as we have to discuss in the lecture, the crystal structure of any sample or nanoparticles we have to identify on the basis of by the use of XRD, and we know that XRD based on the Bragg's law. Okay, and technique based on the concept of quantum tunneling. So, which of the following technique used for the based on the concept of quantum tunneling? FTIR, based on the vibration of atoms in a certain space, and scanning microscope is based on the scattering electrons, scatter electrons, secondary electron, and transmission electron microscopy based on the electron being passed through the thin section of specimen. Okay, so definitely the scanning turning microscopy based on the concept of quantum tunneling. Okay, so the correct option is A. Okay, so these all technique we have to use for the characterization of technique. So you have to focus particularly on the application part along with the principle of each technique. Okay, so you could be do better in the field of synthesis of nanoparticles or characterization of nanoparticles. Okay, thank you everyone.